Hey guys, here's your do now. You can pause the video and try to answer the questions. Okay, you should answer the do now. Number one, what is a supersaturated solution? This is a solution that has more solute dissolved in it than it normally would. Okay, number two, how do you make a supersaturated solution? So you have a saturated solution, you heat it up, you add more solute, then you cool it back down, and then that solution now has more solute dissolved in it than it normally would at that temperature. Okay, so from last class, remember we did those experiments, and it's all getting at the idea of what are the best ways to increase the solubility of a solid in a liquid. Okay, so there's three ways we can do that. We can do agitation, so shaking or stirring something. We can heat it up, making the particles more mobile and are moving faster. And we can increase the surface area, meaning we're going to break it into smaller pieces. Okay, so we're going to look at these right now. So how can we increase the surface area? Okay, we can smash it and make it in smaller pieces. So which has more surface area, our sugar cubes or our granulated sugar? You can think, remember the surface area is the area of it's the surface that's shown here. So if we have this sugar cube, only the surfaces around the cube are a part of the surface area. But the same amount of sugar, granulated sugar, each of these little particles has surfaces all around it. So there's actually more surface area in granulated sugar, even though it's, the particles are smaller. Okay, you can think about it here. The surface area is interacting with the water molecules, but when we break it up, we're increasing the surfaces, so it's going to have more surface area. And that makes it dissolve faster because water is able to interact with more parts of the solute. Okay, so if we're increasing solubility in solids, it's actually different for the solubility in gases. So gases can also dissolve in solutions. And the classic example is like soda. It's carbonated, it's got carbon dioxide gas dissolved in it. Okay, so for solids, we increase the agitation if we want to increase solubility. We stir it. We stir our sugar to get it to dissolve. But with a gas, we decrease agitation. Okay, and you can think about if we shake up a soda, what's going to happen? The gas leaves the solution as bubbles. So that means that gas is coming out of the solution and it's decreasing its solubility. Okay, for solids, we're going to increase the temperature and it's going to make it more soluble because the particles move faster. It's making it more like a liquid and it's able to interact faster and dissolve faster. Gases, actually the opposite is also true. So gases are always going to be the opposite. We are going to decrease the temperature to make it, to increase the solubility. Again, we can think about sodas. So if we have a cold drink versus a warm drink, actually the reason we keep it cold is because it keeps that carbon dioxide, those gas bubbles dissolved in the solution more. And we're going to have more of the carbon dioxide dissolved in the solution than compared to a warm soda. Okay, pressure can also play a factor as well. So you can think about a can of soda is pressurized. So before you open the can, it's got all that gas dissolved into the solution, but as soon as you open it, you're decreasing the pressure. It also decreases the solubility, and that's why when you open it, the gas comes out of solution. So when we have gas dissolved in a solution, just like when we have a solid dissolved in a solution, we don't see the particles. Only when they're coming out of the solution do we see those bubbles. So increasing the pressure, opposite here, is also going to increase the solubility. You might have seen these pump cap fizz keepers, and the idea is that if you have a 2-liter soda, you can screw on the fizz keeper and pump it in to increase the pressure to keep it from going flat and keep the solubility increased. Okay, remember we looked last unit at our phase diagrams. Okay, so we can continue to look at this with our gases here. So if we look at our gases, if we're decreasing the pressure, it's making it more like a gas. If we increase our pressure, it's going to make it more like a liquid and therefore stay in solution better. Okay, today we're also going to talk about solubility curves. This is a graph representation of our solubility in a solution. So it tells us how much or how many grams of something you can dissolve at a certain temperature. Okay, and it depends on the temperature, right? Because if we increase our temperature, we can dissolve more and more of that solution. So the line here shows us how much we would need at a specific temperature to have a saturated solution. Above that is a supersaturated solution, and below that is an unsaturated solution, meaning we can still add more to make it saturated. Okay, so here's an example where we're practicing interpreting this graph. So pause this video and try to answer these questions. Okay, for number 1, what is the solubility of NaCl sodium chloride at 30 degrees? So how would we do this? We go to 30 degrees, we go up to the sodium chloride line, and we look at the solubility. And this is saying we would have about 40, maybe a little less, maybe about 38 grams of sodium chloride. But at 80 degrees, it's slightly higher, maybe 39, but very similar. Okay. What is the solubility of KNO3 at 30 degrees? So this one, we go up to the KNO3 line, which is blue at 30 degrees, and it's about 45 grams. So we can dissolve more of that in the solution than we can the sodium chloride. Okay, number 4, what about at 70 degrees? So this really depends on the temperature. So if we go 70 degrees, go all the way up, we get about 150 grams can be dissolved at 70 degrees. Okay, the solubility of K2CO3, that's the purple or magenta line at 30, is about 110. And then at 100, it's about 150, maybe 155 or so. Okay, so this is how we interpret this. This tells us how much we can dissolve in the solution to make it saturated. Okay, so let's think about one more example. If we have a lake and we're wanting to put fish in the lake, but we have to think about fish breathe, and they breathe oxygen gas, and that oxygen is dissolved in the water, and it's dependent on temperature. Okay, so here we have different areas and we have different temperatures. So that also affects how much oxygen can be dissolved. So we have these different temperatures. This is the solubility of oxygen at those different temperatures. Okay, so if we were to graph this, let's see, we had 0.2. Okay, so we got 0.2 solubility at 5 degrees. So if we have our graph, we can, at 5 degrees, it can go to 0.2. At 10 degrees, 0.1. And 15 degrees, we have 0.25. Oh, oops, I did that first one wrong. That's 0.02, not 0.2. So that's going to be even smaller than 0.1. So that's going to be way down here. Okay, and then we can connect these lines. Okay, and now we're going to look at some different fish. Okay, so we have this first fish, the snapper. The temperature required is 10 degrees Celsius, and oxygen is required 0.15. So 0.1 is how much we have. So it needs more than what we have. So it would not be able to survive, and it would die. Okay, this next fish is required to be 5 degrees, and it needs 0.03, again above our threshold, so it would also die. The goldfish at 15 degrees, it needs 0.2, so that's fine because we have that. So goldfish would be able to survive. Pike, 10 degrees Celsius and 0.08, that's again below, so it's in the unsaturated range, so it would still be fine. So these two would not survive, and these two would survive. This is just an example of how we can apply this information. Okay, so this is what we learned today. We learned about the 3 factors that affect the solubility for solids, and the 3 factors that affect solubility for gases, and solubility curves. Your assignment for today is that there are two things. There's a solubility curve worksheet, and then there's a ticket at the door about solubility. So those are your two other assignments for today. Bye, guys.